I'll create two submission links. One is just to upload all the videos that you generate so that if there is any good video, I can use it as promotional material for the next semester or next time. So please feel free to upload any video that you think is interesting. Just upload it. Don't worry about analysis or polishing it. That's just for me to look at it and see if something interesting is happening. The other link will be the actual submission link. Under that, for each group, you can upload your video, Excel sheet, and like a optional video summary that the three of you can narrate what's going on. And essentially, that's your submission, which will be scored. Okay. And next week, I will release a scoring rubric, which will give you an idea of how the grading is going to be done on a scale of 0 to 20, and what will help you get to 20, 15, 10, 5, or 0. Just giving you, I'm not going to be too granular about this, just giving you these broad scores. Okay. And this whole exercise is to see effort more than perfection. So if there is a lack of effort, you can take it for guarantee that you will get a low score. But you did everything, maybe you were missing a little trick or you didn't realize something, but there was genuine effort, you are likely to get a good score. Okay, so don't be worried if you didn't reach the finish line. It's about trying, okay, and trying sincerely. Who else hasn't spoken? Isaac? You're in who Kelsey speak. Okay, you, same thing. Malaki, you are Christina's team. Okay, she already spoke. So everybody decided something. Okay, so and that's it. Today, instead of participation, I'm going to do attendance. So those who are here now, you get points. Those who aren't here now, you get a 0 for attending today. Okay. So let me make a note of that while I teach, when I do examples, I'll make a note. Lucky guy. Okay, so my plan for today is to do 2 examples with scaling analysis, wrap it up, and then move on to the last topic in the course. As far as exam 3 is concerned, I wanted to get this out much earlier. So exam 3 will again contain 5 problems. 2 of them from scaling analysis or module 6, and 3 from, again 2 from module 7, which is what we are going to start later today, and 1 problem that combines both. So, and as usual, there will be 2 easy things that are reasonably easy, and 2 that are average, and 1 that I call challenging. You can bring up to 3 sheets of notes. I will provide necessary handouts. And of course, calculate. What I plan to do is, I will post suggested problems, about 15 for each module. So what I suggest is, you can expect questions that are very similar to the suggested problems. It will be in that type. There will be modifications, there will be slight changes to make it interesting, but I strongly suggest that you do the suggested problems both for module 6 and module 7. So I'll post them as 2 PPT files. I'll also post a mock exam, which we will discuss at the last lecture. Okay, the lecture before the exam 3, which is our.
So it's going to be the last day of school or last day of class. Are we going to do it?
The last day of lecture is your exam. This is the lecture before that. Okay. You want the dates? I don't want to confuse you. It's all in the syllabus. We'll stick to that. Yes.
It's still gonna be April 28th.
Yeah, last class meeting is your exam 3. And the lecture before that is the discussion of the mock exam. Yeah, I was going to talk about final. Is it clear about exam 3? Are we recording this? Yes. To be clear about exam 3, so exam 3 is on, like you said, April 28th, I think. And you need something, you can count on Microsoft to irritate you. I won't say dates, just look at the syllabus, it's on there. Okay. So for the final, it is comprehensive. Okay. It will test you broadly on the 3 parts of the course, which is part 1, we'll call it whatever was for exam 1. And part 2 was whatever for exam 2. And part 3 is whatever we had for exam 3. So you have to study. Yes.
When you say 2 easy, 2 average, 1 challenging, does that mean there's 1 easy and 1 average for module 6 and then 1 easy?
No, I won't give you that split. It'll be, I think I'm telling more than what most instructors say.
Yeah.
I'm not giving you more information. So there will be 3 parts. There will be 3 problems, 1 for each part. It will be fairly lengthy, so you can expect each problem to take you about 30 to 40 minutes. And the total duration of the exam is 2 hours. Okay. You can bring up to 6 sheets of notes. Okay. I'll post a mock. I'm not going to discuss it. It will not be that new content. You just have to see the mock and try to work it out. Maybe I'll provide the steps of the solution. Sorry, mark will be. In the final, it's not going to be like easy, challenging or anything. My hope is to keep all 3 of them of average difficulty, so that you get a final chance to score. Not going to make it tough or too easy, but it will take you about 30 to 40 minutes if you know what you. Okay. And a little bit closer. That is, once I prepare the final and put it away, I will have a clearer idea of. I'll make a short list of topics. Like for example, in part 1, what did we see? We saw statics and Bernoulli equation. Okay, so I'll try to put exactly what topic you're going to get for each of these 3 problems, and it's possibly that if you just study those 3 topics or 6 or 3 or 4 topics, you should be okay. And I'll do that once I have thought about the exam. But it's going to format is 3 problems, 2 hours, up to 6 sheets of notes, covering the entire course.
May 7th from 8 to 10.
May 7th from 8 to 10. Awesome. Okay, without spending more time on this. Let's do the two examples planned for scaling analysis.
The funds will be in this room, correct?
That I don't know. You have to check the registrar website. I don't want to say something by assumption. Once I check it, I can put it on an email, or you can also check. Let's do problem 12, please. Problem 7.12. Problem 7.12. The pressure rise delta P across a pump can be expressed as H can be expressed as delta P equal to function of diameter, omega being the speed of rotation, viscosity, and flow rate through the pump. Determine a suitable set of dimensionless parameter to express this dependence. So you need to reduce essentially, if you pick three variables out of here to non-dimensionalize, you're going to be left with only one more, and then you also have to non-dimensionalize the pressure drop. Okay. So just to recap, I'll do this problem. Then next problem maybe you can try. If you're done writing the question, I can pull back. What is what? We good? Yes. Okay. Start here. So we have delta P equal to a function of diameter, the rotation speed omega, viscosity, and what was the other variable?
Q.
Q, flow rate.
It wasn't viscosity, it was density.
Density. Right. Density and omega. Okay. So what's our first step?
You could do L reference and that's the given.
Thank you. So step one, choose reference, mass, length, and time. So L ref is easy. L reference can be the diameter because that's the only length scale that is involved. And then we want reference time. Now, if you think about omega, omega is rotation speed, usually measured in units of rotations per minute or rotations per second, or sometimes even radians per second. If especially omega is written as 2 pi times rotational frequency.
How did you know radians?
So you can consider different situations. That is, in your thinking, you might record omega as per second. Somebody else may record it as 2 pi times the frequency. So it's a choice, it can vary. So let's say we pick this one. Oh, sorry, let's say we pick this notation where omega is expressed as rotation per second. So the reference time would be inverse of omega, which would have units of seconds. So 1 over the frequency is a good reference scale for this problem, right? And then reference mass, M reference, you can think of density, which has units of kilograms per meter cube, multiplied by L reference cube, which has units of meter cube will get a quantity whose units is kilograms. So M reference, a good choice for M reference would be rho times D cube. So we have already used the diameter, we have used the omega, we have used the density. So the only two remaining quantities on the input side, Q, and the output side, delta P. So that need to be non-dimensionalized. So then step 2 would be to non-dimensionalize delta P and Q in terms of L ref, T ref, and M ref. So let's take Q. So take Q, consider the dimensions of Q. What are the dimensions of Q? What is Q? Volume flow rate. How do you think of volume flow rate? Volume per time, right? So that would be L cube T to the minus 1. I mean, you should be able to say what the quantity is. Volume flow rate is nothing but volume flow per time. So it should be a length cube divided by time. So then Q divided by L ref cube times T ref to the minus 1 should be dimensionless. So Q divided by D cube times omega inverse the inverse. So this is Q divided by omega D cube is the non-dimensional form of Q. So we have kind of brought it down to delta P equal to a function of Q divided by omega D cube. We still have to non-dimensionalize this. There is still one more step left. So then take delta P, consider the dimensions of delta P. And what is delta P? Pressure rise, or in other words, delta P should have unit of pressure, which is Pascal, which is Newton per meter squared, which is kg meter per second squared divided by meter squared, or the dimensions of delta P is mass per length per time squared. See, the thing with scaling analysis is there is nothing else, there is no other tricks here. Every problem starts with a statement of what depends on what all. Then you go through, choose the reference scales, non-dimensionalize everything that is left behind, and then you end up with a non-dimensional equation. That's so for delta P divided by M ref multiplied by L ref inverse multiplied by T ref to the minus 2 should be dimensionless. Can I erase this side? Like this side, this portion? Yeah. So delta P divided by reference mass, which was rho times dq, multiplied by reference length, which is d to the minus 1, multiplied by reference time, which is omega inverse to the negative minus 2. This is delta P divided by rho d squared omega squared. So the relationship, which was originally delta P equal to a function of the d omega density and q, now becomes delta P divided by rho d squared omega is a function of q divided by omega d cubed. So what? What is the point of writing this expression like this? Any thoughts? Why should we do this and write it in this form instead of the original form?
Is it? Now it's like unusable algebraic equations and plug and play to solve for variables.
You can still, neither this equation nor this equation can be used to solve for anything. It just expresses the relation between pressure rise and everything that it depends on. It still expresses a relationship between pressure rise and everything else that it depends on. It still is not any more functional than this one is. The real utility of such a relationship comes when, think of a pump. Okay, let's say you have a pump that you're trying to test. How you test a pump? Let's say you have a flow meter which can record Q, and you have a pressure gauge that gets you delta P. So when you pick a pump, what are the factors that just are already decided, and what are the factors that you can vary in this experiment? When you buy a pump, what are things that the manufacturer puts a label on and that's something you cannot change?
The diameter.
The dimension, that is the diameter is already fixed. And usually pump manufacturers also tell you at what speed their vane or blade or whatever the rotating component is. This number is fixed. Unless it's a variable drive, it's a number that is fixed. Okay. The fluid that you are handling, air or some gas mixture, or if it's a liquid pump, water, oil, whatever it is, that is something you can vary depending on what's allowed in the pump. The way you adjust the pump is either you set the flow rate and measure the pressure rise, or you set the pressure rise and measure the flow rate. So you can consider this as an input and this as the output or observable, or the other way. It depends on the pump control. Okay. if you are planning an experiment, what this relationship tells you is you don't have to vary Q, omega, and D separately. Doubling Q is same as halving frequency. Or if you let's say double the diameter, if you double the diameter, if you replace D with 2D, replacing D cube with 8D cube. Doubling the diameter is like making the flow rate 8 times smaller. Okay, so this type of a ratio allows you to plan combinations of this number. Instead of worrying about how to vary three quantities independently, you just have to vary this one ratio independently. You just have to map. If you're plotting the data, you would plot delta P over rho D squared omega divided by Q over omega D cube. Something like this. If you see some pumps or textbooks, they'll give you this like an operating chart. So if you measure the pressure drop, which is usually the easier thing to measure, you can use this as a lookup chart to see what must be the flow rate. So you measure the pressure drop, maybe your fluid is air, density is 1.2, everything else same, you can read out what your flow rate is. Let's say your fluid is not air, but let's say it's argon gas, which is slightly heavier than air. For the same pressure drop, if density were different, you would get a slightly different flow rate or the other way. So the entire utility of this type of scaling analysis is to reduce direct relationships into non-dimensional relations so that any data that you generate, it could come from an experiment or a simulation, can be analyzed more efficiently, and you can save on the number of trials you need to. You don't have to probe these three quantities separately, you just have to probe this ratio together. Okay? That clicking? Yes?
In the experiment, what would you be changing? Just the change in pressure and flow rate?
Again, that depends on your pump. Most pumps, what you will do is you will put a valve here and you set flow rate and you measure what is the corresponding pressure drop. So you will say treat Q as a input by setting a valve and a flow meter to set a value of Q, and then take what delta P you observe for that pump. And as we will see in the next module, delta P is usually something that's determined by the flow rate, the density, viscosity, and the geometry of the pipe or tube or the structure. Okay. So usually this is an output and this is an input for pump test. Okay.
So will we have to do this with assigned values, or are we only going to do it with kind of just making the equation? You know what I mean?
I know, I don't understand what you mean.
Like, will we have like values to test from different ratios? Will we be given different ratios to test from? Or are we just making like this?
So any problem without reference to the actual numbers, all we did was to take the quantities that influence or that may influence this quantity and turned it into a non-dimensional relation. Then when you go out and collect data, that's when you will know actual relationship between these two quantities, between this ratio and this ratio, whether it's a linear or whether it's not correlated or it's downward or quadratic, everything that you know only from your data. This is pre-data. Before the data, how should you plot them? That's what we are really learning here. Yeah.
So these ratios, like I guess in terms of an experiment, are we kind of assuming that at the same ratio, regardless of the actual values, it's going to behave pretty much the same?
Exactly. We believe that if you have two pumps, okay, and they differ from each other in the diameter, and let's say this value is 4. Okay, so Q over omega d cube is 4. Okay, so this is, let's say for pump 1, this is true. Between pump 1 and 2, the only difference is, let's say, the diameter. So Q2 divided by omega 2 multiplied by diameter, which is, I'll call it D2 cube. If I want to match this at 4, okay, if I make the diameter half, if this is D1 cube divided by 8, that would mean Q2 must be 8 times Q1. So if you did an experiment, you collected data at all these ratios, if you know the ratio, you can extrapolate from 2 centimeter diameter to 4 centimeter, or your working fluid density change from 1.2 to 1.7. You can easily make those shifts if you know this relationship. That is the whole purpose of scaling analysis, to reduce everything to ratios so that you don't have to probe it at every condition that you will ever encounter.
So you wouldn't have to like try to measure something acting on like a whole dam when you can just do a scale. That's the same ratio.
Yep. In fact, most of the times when objects are too small or too big, especially too big like an aircraft or a car, they create scaled down models and measure it on the scaled model and then extrapolate it back to the original structure. It could be a bridge, it could be a plane, it could be a car, anything. Okay. Good questions. So let's do one more problem. I think over time this will come to you. Problem 7.29. So Christian, I got your email with the video. I don't have it logged in here, but Tuesday, first 10 minutes, I'll play all the videos that I get by that point. Everybody who wants to show their video to me, send it to me. I'll just play it in class on Tuesday, first 10 minutes. We'll quickly see how each of you are doing. Okay, like a status update. It's not compulsory, just for fun.
729, please.
29, problem 29. A jet of liquid directed against a block can tip over the block. Assume that the velocity needed to tip over the block is a function of the density, the diameter of the jet, the weight of the block, the width of the block, and the distance d between the jet and the bottom of the block. Determine a set of dimensionless parameters for this problem. From the dimensionless parameters by inspection, use the momentum equation to determine an equation for V in terms of the other variables. We'll skip part B. We'll just do part A just to do the dimensionless parameters for this problem. Each of you, for your respective project, that is the funnel problem, you should do your own version of scaling analysis. Like what I tried the last time, you should do your own version of scaling analysis just to see how you can plot your data of H versus T or the flow rate versus time. So if you made a note, please let me know. We'll start here. This is problem 7.29. So we have the velocity required known to be a function of a long list of quantities, starting with density, diameter of the jet, d, the weight of the block, the width of the block, weight, width, and the distance of the jet from the bottom of the block. Yes,
What would be used for T reference?
we are going to talk about. You can tell me your thoughts. Usually, you have a question, you will have some opinion. Say that.
I guess you use velocity. Yes. Assume we want that dimensionless.
So if you look here, this is a length, and so are these. So for L reference, we can choose any of these, but you should also think about what's the most intuitive choice. What's the most important dimension that determines this problem? Is it the diameter? Is it the width of the block? Or is it the height of the jet? Diameter. Because if the jet were like very wide, it doesn't matter how much D is or how much B is, it would overpower the block anyway. So diameter is a critical dimension. And usually the reference length is best chosen as something that's critical and not something that's kind of secondary, tertiary importance. Okay. So like for your own body, what's the most important metric that doctors will measure when you go to the clinic?
Blood pressure.
They measure a weight, they measure blood pressure, they measure body temperature. So these three, depending on like these three are critically the important numbers. Nobody measures your as you walk in immediately. Nobody measures a secondary quantity like the size of your face. It's not a very important quantity. So I'm just saying, pick the most important quantity. Okay. So then, if you pick LREF to be D, then you can write B over D and D over D. That's easy. Just that non-dimensionalizing the remaining lengths based on the chosen reference. Okay. Can I take this back? Are we good?
Yeah.
Because in the video, if I have this screen, the video quality. Okay, what do we have next? This density rho, which has dimensions of mass per length cube, and then weight, which is what? Newtons. Newtons is mass length per time squared. So we have mass per length cube and mass length per time squared. Okay. So between these two, we need to pick two quantities, or we need to define what would be our mref, the reference mass, and tref, our reference time. How will you do that? One quantity has only mass and length. Pay attention, please. So the choice for reference length was very easy. Kenzie, are you having difficulty in reading the board? Can you come forward 2 rows, please? Are you also having difficulty?
No, I'm just confused. Why does the width have a time?
Come again?
Why is there T with?
That's the weight.
Oh, wait. Okay.
That is weight, not width. Yeah. Thank you. Yeah, I'll wait till you settle.
So I would think, our only option for a T-ref is the weight. So I'd probably be best for our MREF to be density.
Very good. So what he's saying is this contains only mass and length, whereas this is the only term that contains time. Obviously, Tref has to depend on W. it has to scale with W. So if you take density, okay, so density divided by mref times Lref to the minus 3 should be unitless. That's the question, or that's the requirement, right? What is our Lref? Lref is D. That's like saying rho divided by mref times D to the minus 3 is unitless. Or that's like saying rho times D cube divided by mref must be unitless, which simply implies the mass reference can be rho times D cube. So M reference is mass rho times D cube. So we have our L reference. Mass reference is rho times D cube. Nick, can you tell us the next step?
So if we have those, we can use that to find our T ref. But because so we have to get the reciprocal of it.
Right. So you're saying it should involve some ratio of density and weight,
Yes.
right? So let's do that. So I have weight, the dimensions of weight being M, L, T to the minus 2. Okay. So that's like saying weight divided by mref multiplied by Lref multiplied by Tref to the minus 2 must be unitless. So that's like saying weight divided by rho D cube multiplied by D multiplied by Tref to the minus 2 should be unitless. Okay, so that's like saying Tref squared multiplied by W divided by rho D to the 4th should be unitless.
You get rho D 4 divided by W square,
Yeah.
the square root of that.
So this is basically saying rho D to the 4th divided by W with the square root should be equal to Tref. Or I'll write that as Tref equal to diameter squared multiplied by rho over W. So here was our original relationship, velocity equal to a function of density, diameter, weight, width, distance, which we can now write is a function of, we have already used rho dw. So this is a function of b over d, d over d. We still have to non-dimensionalize velocity. So what is velocity? The dimension of velocity is length multiplied by time inverse. So that's like saying velocity multiplied by d times Tref inverse should be unitless. So velocity multiplied by d times d squared over square root of rho over w be unitless. Or v divided by d cube times rho over w is the non-dimensional velocity. So this function becomes v over d cube times square root of rho over w is a function of b and d ratios. So this is the final step in your exam, where if you are given a scaling analysis problem, you reduce it to a non-dimensional form such that both sides have only dimensionless ratios. Yes.
T ref was inverse, so substituting.
Oh, the inverse of this. Inverse of this. So I made a mistake there. Thank you. So that would be, I'll write one more step, v multiplied by d over 1 over d squared, square root of w over rho. So that is v multiplied by d times square root of rho over w. b d b d square root of rho over w. Sorry, thank you for catching that. Clearer on the video. Is how you should think of the problem is you do the experiments for a range of these width and height ratios, and then you plot them in, you plot the velocity normalized by two things. One is it takes into account the weight of the block as well as the density of the fluid. Okay. Listen up, please. Take a moment, listen up. Every problem I'm going to try to make the same explanation. So let's say we take this quantity v d square root of rho over w. We'll give it a symbol phi1. Listen up, please. Take a pause. Okay. You do an experiment and get a value for phi1. Whatever that value is, let's say 4, 10, some value. Okay. That experiment was done with a fluid like air, whose density we'll say is 1.2 kg per meter cube, and a plate or block with weight, with mass, let's say 1 kg. Okay, we'll keep, we do, or we want to know what will be the p value in another situation where density and weight are different, but the ratio pi 1 has the same value as before. Same value as before. Do you get the context? You do one experiment, you get a certain value of velocity in that experiment. You use a certain jet diameter, density of the fluid, weight of the block, and you got a certain value of pi 1. Until then, this is the story. Then you think of another situation and you want to know what will be the velocity value of that situation. The only connection between that situation and the where you did the experiment is they both share the same pi value. Okay, so we'll say situation 1 at which the measurement was done. Okay, you measured B1, the velocity, the diameter is B1, the density is rho1, and weight is W1. Okay, for example, this is like 1.2. For example, this is like 1 kg. And then situation 2, at which you want to know the V, but without doing a new measurement. So in this situation, you want to know what is V2. Let's say you have diameter D2 that happens to be same as D1, and you have rho 2, which is, let's say, a gas that is twice as dense, which is 2 times rho 1, and then you have W1 or W2, which is 2 times the weight of the first block. Okay, these two situations have the same pi 1 value. That is the connection between them. You select if it so happens that these values lead to the same pi value, then you can write P1 T1 over rho 1 W1 equal to V2 T2 over rho 2 W2. If it so happens that these ratios are same, then you can use V2 equal to V1. If the ratios are same, okay, but by varying diameter, density, and weight in a certain proportion, you are still able to maintain the ratio. It will allow you to solve for V2 in a new situation without having to do a new experiment. That's the original idea behind scaling analysis. You reduce your entire problem to 1 or 2 dimensionless numbers, and you do an experiment in air, extrapolate it to oil or water or whatever your fluid is, so that cataloging information becomes easier. Okay, I'll try to give you one more example. So when you were few years ago, when you were selecting schools for your undergrad, what is one common metric students use? They look at faculty to student ratio. Like how many faculty members per student. So you try to think about, if you think Memphis, you think how many faculty members per student or how many students per faculty. When you compare different schools, there are so many metrics, but faculty to student ratio is one common metric that students use because it's quite indicative, right? So there may be many ratios, but if you try to match at least one of the ratios, you'll be able to extrapolate conditions. Okay? Let's do more examples. I hope each time I can come up with a slightly different explanation or way to explain scaling analysis. Okay. Questions? I see a lot of stares and disapproving looks. Can you tell me something not clear? No? Okay. Try to apply this in your project. Do a scaling analysis of your funnel problem. Try that. Okay, just gets your hands soapy. Are we ready to move on? Okay.
So this is the solution to part B.
This is the solution to part A. I didn't discuss part B.
We like to see something like part B in the exam.
Part B, let's see here. Okay, what is part B? Yeah, I mean, not on this exam. It could be on the final exam. It's saying use momentum equation. That's basically module 2 control volume analysis to derive an equation for the velocity or force in terms of the to topple it. So this is totally a problem that can be come up in the final. Okay, I've been telling you about how to plot experimental data, right? So let's look at problem 7.38, which exactly does that and hopefully gives us more chance to understand this. Problem 7.38. Please take a look, make a note, we'll discuss it. 7.38.
So would it be better to choose A1 or A2 here since A1 is changing, the A2 is constant?
I mean, usually that is in practice, it's always the original cross section, just like you do in your strain analysis. You take the initial length as your reference for engineering strain. We take the inlet cross section as the reference for everything else that happens downstream. Because when you run an experiment, you would usually be controlling V1 across A1, and everything else that happens after that is something that is a consequence, not a cause.
Yeah, but in the problem, it shows a ratio of A1 over A2 instead of A2 over A1.
That is okay. You can invert 0.35 and get a A2. It's again in fluid mechanics, what is upstream, what is downstream can keep changing. If you run the experiment the other way, if instead of calling it an expansion step, you can call it a contraction term. So both are okay. So the pressure rise delta P across the abrupt expansion can be expressed as a function of the two areas, the upstream and downstream cross sections, fluid density and upstream velocity. The experimental data is given to you. Plot the results of these tests using suitable dimensionless parameters. With the aid of a standard curve fitting program, determine a general equation for delta P and use this equation to predict delta P as a function of the flow, delta P for water flowing through an abrupt expansion with an area ratio of A1 over A2 to be 0.35. P1 equals 3.75. Now I see why you are asking A1 over A2 or A2 over A1. But the original data itself is presented to vary A1 and not A2. The original data is presented as A1 as a delta P as a function of different A1 values. So A1 is the natural choice for the reference. So, okay, before I pull this down, for the curve fitting part, I will use Excel and show you the result quickly. But look at this first equation. We have two areas, a density and a velocity. Among these two areas, how will you select the reference length scale? Area is not length, area is length squared. So how will we select the reference length scale even if we take A1 as a reference area? Square root of A1. That will be a length, right? Square root of A1. Can I take that as a reference length? Yeah. You know what? I'm going to revert back to A2 because A1 is treated like a variable, but A2 is a single number. It's more convenient to have a reference that doesn't keep changing. So A2 is the better choice for reference length. Okay, so let's start the solution here. What are the fixed quantities? A2 and V velocity or V1, and we are also given density to be fixed. Fixed values. This is problem 7.8. Okay. So we are given the original data is given in terms of delta P versus A1. Okay. We need to express this in terms of delta P divided by something and A1 divided by something, or let's say A2, so that you get a non-dimensional plot. That's the goal. So starting with reference length, we can choose reference length to be square root of A2. Square root of area 2 cross section. And what is a good reference time? That would be V1 divided or V1 multiplied by, V1, square root of A2 divided by V1. How many of you look at this and go, yeah, okay, that makes sense. I skipped a bunch of steps.
I got the, wait, hold on. No, I got that. Never mind.
Length divided by velocity should give you a time scale, right? Length divided by velocity. This is the length divided by a speed should give you time. And what is a good reference mass? We already have density. So density multiplied by square root of A2, the cube. Or that is like saying density times A2 to the 3 by 2 power should be a reference mass. So we have the relation delta P is a function of A1 over A2. We have already used up one length. We have already used up diameter and velocity. So it's only this, and then we have to think how to non-dimensionalize the pressure drop or pressure rise. I'm going to stop sharing for a second so that in the recording it's clearer. I'll bring it back. So how do you move to the next step? How do you non-dimensionalize pressure rise? Right. So if you're not sure, always start with the dimensions of the quantity, which is if you're not sure what the dimensions are, write the unit Pascal, which is Newton per meter squared. Newton is kilogram meter per second squared divided by meter squared, which is then mass per length per time or per time squared. So that's the dimensions for pressure drop. So delta P divided by m ref multiplied by L ref to the inverse multiplied by T ref to the minus 2 should be unitless. So delta P divided by rho A to the 3 by 2, A2 to the 3 by 2 power. L ref is A2 to the half, and then I have to invert it. And then T ref is A2 to the half divided by V1, and I have to raise it to the power minus 2. Given my track record with algebra, I just do one more step. A2 to the power 3 by 2, and then I have A2 to the power minus half, and then I have A2 to the power minus 1, and then I have 1, or I have V1 squared. V1 squared. This is nice because all this goes away. So I have delta P divided by rho times V1 squared. Anybody recognize the quantity half rho V squared from long time ago Bernoulli equation? We used to call it some name. Dynamic pressure. So delta P being scaling with rho V squared should not come as a surprise because it is half rho V squared is what we call dynamic pressure. So it should have the same unit as delta P. So coming back here, if we plot delta P divided by rho V1 squared as a function of area ratio, we should get a non-dimensional plot. Can I bring back the board here for 1 second? I'm sorry, the problem. This problem gives me a chance to show in numbers what I've always been saying. Look up, please. So you did an experiment. You did this data collection, that is for delta P, you had different inlet areas and you measured delta P in each case, and you had this data collected from your lab run, okay? Instead of plotting it as delta P on the y-axis and A1 on the x-axis, we are going to plot it delta P over rho V squared on the y-axis and A1 over A2 on the x-axis, okay? Once you do that, you can use that relation to get the value for any area ratio in this range between 0.1 to 0.61. Okay, so let me quickly do that.
So the values in this situation are constant, density and I guess velocity are constant in this situation.
Yeah. Yeah, in this situation, they are given, that's why we took them as reference values. Okay, so I'll go back here. So if you have your laptop with you, you can also try plotting with me. 0.1, 3.25, 0.25, 7.85, 0.37, 10.3, 0.52, 11.6, 0.61, 12.3. Okay. Then we'll calculate A1 over A2, which should be unitless. So this should be what is our A2 value?
1.25.
1.2, yeah, 1.25 square feet. Thank you. 1.25 square feet, and V1 was 5 feet per second, and density rho was
1.94 slugs per square feet.
yeah, 1.94 slugs per cubic feet. Okay. So A1 over A2 would be the A1 value divided by A2, which is just a single number. So I get this. And then delta P divided by rho times V1 squared. That would be delta P divided by density times velocity squared. So the first type of plotting of the raw data will be between delta P and area, which gets you this. Okay, the second plot we will do is between the two dimensionless numbers, which is this. So if we add a trend line, which is reasonably a second order curve, second order curve. So this is your relation between the ratio delta P over rho V squared being Y. So I'll replace that. Delta P over rho times V1 squared. And what is our X? X is A1 over A2. Please. So this is your equation, which is a function of A1 over A2. So previously, when the data was originally presented, you are given delta P as a function of A1. This way of plotting not only considers the quantity that was varied, which is A1, it also considers the quantity that are specific or fixed for the experiment, like density and velocity. So if you just keep everything same, that is, if you keep area ratio same, if I give you this plot and then ask you to compute, let's say, the pressure drop when A1 over A2 is 0.35, what would you do?
Okay, 0.35.
We will plug in 0.35 or whatever this ratio is and calculate the number. Okay, so let's do that. So let's take this equation. I'll copy this so that I can put it over here. Okay, so we want to compute delta P when A1 over A2 equals 0.35. And how you would do that is delta P divided by rho times V1 squared. That ratio is a function of A1 over A2, which is 0.35. So to plug it in, I'm going to write minus 1.1071 times the ratio squared plus 1.0754 times this number minus 0.0108. So the answer is supposed to be 0.2297. Are you with me so far until this point? Yeah. This is not delta P. This is not delta P. This is the ratio of delta P over rho V squared. So if I want delta P, that would be the ratio multiplied by reference density rho times V1 squared. So I would have this quantity multiplied by my reference density multiplied by my reference speed squared. This will be in pounds per feet squared. And this is the number. Okay, I don't know why that's not changing. Anyway, so delta P should be 0.45. How to check whether this is correct or not? So where is 0.35? So sorry for the numbers here, they are so tiny. I'll make them bigger. Okay, so where should 0.35 be? It should be between 0.3 and 0.4, somewhere midway between them, right? So if this value is like, what's this value? This value is like 0.29, almost 0.3. Yeah, this 0.3, comma 0.21. Okay, and this value is it's about 24, right? Between 21 and 24, the y value.
Thanks.
Y, I mean, yeah, x value is 0.35, y value is between 0.21 and 0.24, and we are getting something like the ratio being 0.23. That's right about the middle. Okay, then we calculated a value of 0.45 for delta P. Okay, so if A1 over A2 is 0.35, what is A1? A1 is the ratio multiplied by the reference, which is A2. So that's like 0.35 times the reference area, which is 1.25, that is feet squared. Now you can go back to the original data and check for a value of A1 that is close to 0.44, will you get 0.45 pounds per square feet? You can check that. How do you check that? Your data is right here. So between 37 and 52, it varies between 10.3 and 11.6. Right? So for 0.44, what are we missing here? Oh, that's because I made a symbol mistake. I should have been getting 11.2. So for 0.44, I'm getting 11.2. Between 37 and 52, it's varying between 10.3 and 11.6. So considering this is a second order curve, getting 11.2 sounds reasonable. Okay? With me? Yeah? Okay. We have 2 minutes. I just want to make one last point here. For the same delta P, that is for the same A1 over A2 ratio, if I just double the density, what would be the value of the pressure? If I want to know the pressure in conditions where the fluid I use has twice the density, like 1.94 times 2, what would be the pressure? Assuming the ratio is matched. Pressure would double because pressure scales with density. If I double density, pressure should double. If it scales with velocity squared, if I double velocity, what will happen to the pressure? 4 times. V1 replaced by 2V1. So V1 squared is replaced by 4V1 squared. Okay. Anyway, so what I'm going to do, this is where I wrap up scaling analysis, and I have to start module 6 because there are only 3 more lectures left. I'm going to post a list of 15 problems on scaling analysis. I strongly recommend that you work out all 15 of them because two problems out of that 15 with some modification may show up. So if you skip on that 15 and decide to do like, let's say 2 or 3 only, you will not be adequately prepared. So 15 is the bare minimum you could do. Ideally, I would say do all the problems, but that's a lot. But this 15 is what I expect each of you to try. Otherwise, I can't guarantee that you'll be able to do well in the exam. Okay. So I'm going to post a list of 15 for this unit, and then we'll start chapter 8, which is our last on pipe flow. Okay. Thank you.
What day did you say exam three was? Did you say that?
Come again.
What day did you say exam?
I didn't say any day. Look at the syllabus.